Welcome. We're going to begin by talking about complex numbers. And I know that for many of you this is already a familiar topic, but I want to begin at the beginning of what's going to be a long series of videos. So in today's video, I'm going to try to introduce the idea of complex numbers in an organic way. We're going to begin by talking about number systems. These are the enlarging number systems that we are taught as we move through our math education starting in elementary school. That's going to bring us to the concept of the imaginary number, and we're going to talk about the properties of I, which we designate as the imaginary unit. We're then going to move on to talk about complex numbers, and we'll define their addition and subtraction. I'm then going to move on to the complex plane and talk about a geometric concept of complex numbers, which will lead us to the modulus of a complex number, which gives us some notion of length in our complex number system, or size. Okay, so to begin with number systems, these are the increasingly large collections of numbers that you're taught to work with as you move through your math education. And we start from something very simple and we move towards increasingly complex number systems. And I don't mean complex in the technical sense at all, just more complicated. So the first number systems you're taught, the first number system is the natural numbers. These are the numbers that we get just by counting, 1, 2, 3, and so on. The numbers you can literally count on your fingers. That's why they're sometimes also termed the counting numbers. That works well for a while until we need a zero concept. We need a number that expresses the idea of nothing. So once we add the number 0, we actually redesignate this number system the whole numbers. So these are the numbers 0, and then our natural numbers are included in that set. So again, we have 1, 2, 3, and so on. And we continue in that vein for a while until we get to the idea that we need negative numbers. And so once we bring negative numbers into our set of numbers, we call that new set the integers. And so that will include all of our whole numbers, 0, 1, 2, 3, and so on, but also negatives of those numbers. So negative 3, negative 2, negative 1, and our whole numbers. As you see, these sets are getting bigger and bigger, and containing the previous set each time. We then get to the concept of division. And once we have that, we have this concept of the rational numbers. These are the set of numbers, this is the set of numbers that can be expressed as fractions. So that actually includes our integer, any whole number, negative 3, or any negative number, any whole number like positive 3 or a negative number like negative 3 can be expressed as the ratio of that number over 1. So we get all of our integers, but we also get fractions like negative 5 halves, negative 2, 0 is in there, of course. 0 is a rational number. And some of our integers are also I'm just writing a lot of different things in 22 over 7. Okay. Finally, we move to geometry. And once we get to geometry, we have to reckon with things like this, a isosceles right triangle with both legs equal to 1. And then we find that the hypotenuse is the square root of 2 from the Pythagorean theorem. But the square root of 2 was proven by Euclid to be an irrational number, not a rational number. It's not a number that can be expressed as the ratio of two integers, of any two integers. And then we do more geometry, and for example, we find the circumference of circles. I'm drawing a sketchy circle here, but I hope it gets the point across. We have a circle with a certain radius r, and the circumference of that circle is going to be 2 pi times r. And we know that pi is also not a rational number, that if you type pi into your scientific calculator, you're going to get a non-repeating decimal, which is the hallmark of a irrational number, a non-repeating decimal. So these irrational numbers need to be added to our set. These are the numbers that cannot be expressed as the ratio of two integers. And it turns out, actually, that the irrational numbers are an even bigger set than the rational numbers, but we combine those two, and we get the real numbers. So we take our rational numbers, numbers that can be expressed as fractions or as ratios of integers, and our irrational numbers. We combine those two things, and that gives us the real line. In other words, those numbers can be expressed on a continuum, and we can designate points on the real line. So here I'm just starting with our whole numbers. I'm marching out from 0. And this is a sketch, so obviously these distances are a little approximate, but hopefully you get the idea that these are all evenly spaced apart. So we have our integers now, positive and negative numbers. And then we can include some fractions, so a half would be there, let's say. And over here we have negative 2 and 7/8. I'm just writing that as a mixed number. And we also have some irrational numbers. So I'm going to try to graph the square root of 2. It should be around there. Let's see if I can do it. We're going to have important numbers like pi on this number line. And I'll also include Euler's number e, 2.71828, and so on. Very important number for us in this course of videos. So great. So why do we need anything else? We have our number line. Why do we need so-called imaginary numbers? Well, these also emerge quite naturally. As we've already seen, when we do algebra, we're going to find that we need this new number concept of the imaginary number. So, for example, if we have to solve x squared plus 1 equals 0, applying the usual rules of algebra, we'll subtract 1 from both sides of that equation, trying to isolate x. So then we'll have x squared equals negative 1, and I hope some of you see where this is going. To cancel out that square, we have to take the square root of both sides of this equation. And when we do that, the square root and the exponent to the second power, those cancel, and we're left with x equals the square root of negative 1. And there's our problem. The square root of negative 1 is not a real number. There's no place for that on our real number line. Because of the properties of multiplying negative times negative, you get a positive. There's no situation where you square something and you get back a negative number. So what we do is we introduce a new letter, and we call it I, and we just define that to be the square root of negative 1. We call that the imaginary unit. And we're then going to follow through and keep all of our rules of algebra, of arithmetic, everything. But we're going to designate I as the square root of negative 1. So we're going to follow this definition to all of its consequences, all of its conclusions. And when we do that, a few things emerge immediately. So for starters, we've already said that I equals the square root of negative 1. Therefore, that's the therefore symbol, right? By definition, I squared equals negative 1. Square root of negative 1 times square root of negative 1 equals negative 1. Okay. We're then going to use I in representing the square root of any negative number. So, for example, let's finish writing that. For example, take the square root of negative 16. That will equal the square root of negative 1 times the square root of 16. And here I'm just making use of the rule that if two things are multiplied together under the radical sign, that you can separate them into different radicals. So we get I times the square root of 16, or 4i. And of course here I'm just using the positive square root of 16. I could have also said that's negative 4i. I hope that's clear enough. Here's another example. The square root of negative 36, that would be equal to 6i. or the square root of negative 2. That would equal I times the square root of 2, and so on. So that's a nice feature of our notation of using I as defined to be the square root of negative 1. Another consequence of our definition of I being equal to the square root of negative 1 is as follows. We know that I to the first equals I. Again, we're just making use of the rule that anything to the first power equals itself. Any number to the first power. So I to the first equals I. That's kind of a vacuous statement, but you'll see where it takes us in a minute. Now we have I squared equals negative 1 by definition of I. Write that down. By definition of I. So what about I cubed? Okay. That would equal I times I times I by definition of raising something to the third power. And now I'm grouping terms. That's going to be I squared times I. And here I'm using the law of adding exponents together. And then I get negative 1 times I, or I get I cubed equals negative I. Okay, I'm going to just continue that process on the right side of the board here. I to the fourth would equal I squared times I squared. That would equal negative 1 times negative 1, which equals positive 1. Okay, so what happens if we continue this process of finding the exponents of I, raising I to different powers? I'm going to make a little chart here, and on the top here I'm going to write the letter n, which is going to stand for our exponent, and I to the n. And we're going to tabulate our results so far. So we know that if n equals 1, I to the first power equals I. I'll write that over here on the side too. And I squared we know equals negative 1, so I'm going to write that here in my chart. When n equals 2, I to the second power equals negative 1. And we already found that I cubed, I to the third power rather, equals negative I. So I'll put that here in the chart. N equals 3, I to the 3 equals negative I. And we know I to the fourth power equals 1. So let's chart that here. N equals 4, I to the 4 equals 1. So what about I to the fifth power? What's that going to equal? Well, I to the fifth is going to be I times itself 5 times. I'll write that out. I times I times I times I times I. That's going to be grouping things together. I'll put ones there just to be very explicit. We're going to group things together like this. That's going to be I to the fourth times I to the first power. And that's going to equal 1 times I, or just I. So we're back to I now. So I'll chart that there. I to the fifth power equals I. Just like I to the first power equals I. That's interesting, right? Now what about I to the sixth? Well, that will be I to the fifth times I. We just found I to the fifth equals I, so that'll be I times I, or I squared, which equals negative 1. And I'm sure that a lot of us are seeing that this pattern is starting to repeat. I to the sixth equals negative 1. I to the seventh equals I to the sixth times I. That'll be negative 1. We just found that, times I. That I to the eighth, which I'll chart in a moment. Let me just chart I to the seventh here. When n equals 7, I to the seventh equals negative I. That I to the eighth will indeed equal positive 1, and so on. The process continues. So there's an interesting cyclical pattern to our exponents of I. Okay, so I'm going to now move ahead. We're going to start talking about complex numbers. Because what have we looked at so far? So far, we have really only discussed numbers that are either multiples of our imaginary unit I or exponents of I. So we've only talked about what might be termed purely imaginary numbers, numbers that are purely in terms of I. Well, we're going to expand this. What about solving another algebraic equation that's going to take us there? What about solving this one? Our equation could be x squared minus 2x plus 5 equals 0. And this is just a motivating example, okay? So I'm going to rewrite it. X squared minus 2x plus 5 equals 0. And you'll see that that doesn't factor. We're going to have to use the quadratic formula. That's the formula that gives us solutions to algebraic equations where our highest exponential term of x is the second power, where we have an x squared term as our highest exponent, our highest degree. So the quadratic formula says x equals minus b plus or minus the square root of b squared minus 4 times a times c. I'm going to just write that there. I'm expanding my radical sign there. 4 times a times c, all over 2 times a. And these a's, b's, and c's, of course, represent the coefficients in our equation. So a is going to equal 1. B is going to be that negative 2 there times x. And c is going to be equal to 5 in this equation. And so then we're going to plug those coefficients in, and we get x equals negative 2. That's going to become positive, obviously, plus or minus the square root of negative 2 squared minus 4 times 1 times 5. I'm going to try to keep my color coding consistent through all this. All over 2 times 1. So now x equals 2 plus or minus. I'm going to do the radical sign on the side here. 4 minus 20 equals negative 16. So it's going to be 2 plus or minus the square root of negative 16 all over 2. I'm going to rewrite that and simplify further here. So we said x equals 2 plus or minus the square root of negative 16 all over 2. I'm going to divide that up to 1 plus or minus the square root of negative 16 over 2, which equals 1 plus or minus 4i over 2. And then carrying that division in the last term, it's going to be x equals 1 plus 2i, or x equals 1 minus 2i. So we've now arrived at a new kind of number that we haven't discussed already. And we call these complex numbers. They're not entirely real numbers. They're not entirely imaginary numbers. They have components of both. And these are also called complex conjugates. And I'll make that clear later on what I mean by that. Some of you may already recognize that term, complex conjugates. So now we have complex numbers. And a complex number takes the following form. It's written in the form a plus b times I. And I just want to point out that a and b are both real numbers. So in a complex number, you have a real number that's not being multiplied by I, and then a real number that is multiplying by I. And those two are added together to form a complex number. So some examples of possible complex numbers, I'm just going to make some up here. 1 plus I, that would be a complex number, of course. Negative 5 plus 2 times I. The square root of 3 minus 7i. 1/2 plus I times the square root of 2. I'm really trying to point out that a and b can be any real number we want. 3 plus I times pi over 2. Those are all examples, and so on. So now we're going to talk about complex arithmetic. Specifically, we're going to talk about addition and subtraction of complex numbers. We're going to define that. So, if we have a complex number a plus b times I, where again a and b represent real numbers, we call a the real part, since it's not multiplying I in this number, and b is called the imaginary part of our complex number. And we set this equal to our variable z, which we often use to represent a complex number. And we call the real part of z the part that's equal to a, and the imaginary part of z is equal to b. And that's how we write it. Real of z, im of z, imaginary of z. So an example here, we could say z equals 2 minus 3 times I. The real part of z then would equal 2. The imaginary part of z would equal negative 3. So why did I go to the trouble of defining that? Because it has a lot of relevance to complex arithmetic. In complex addition and subtraction, when we add or subtract complex numbers, we add the real part and the imaginary part separately. Okay. So I'll do an example again to show what that means, how we do that. Say, for example, we have the complex number 5 plus 2 times I, and I want to add to that complex number another complex number, 3 minus 4 times I. I add and subtract the real and imaginary parts separately. I get 8, adding 5 and 3, minus 2 times I as my result. So what I'm getting at here is that complex numbers have a special addition and subtraction law that resembles vectors. They add and they subtract like vectors. What do I mean by that? Well, let's draw a vector here, recalling that a vector is a quantity that has both magnitude and direction. So we can think of a vector as an arrow pointing in a certain direction. And once we have that arrow, I can draw coordinate axes around it, which is what I'm doing here. I'm saying that vector comes from the origin, and I'm putting arrows here in my coordinate axes, and I'll label my axes x and y. And then this vector can be given components in the x and y directions. So let's say this vector is 5, 2. That means that I can tick off 5 units in the x direction, and I'll just label everything here. So this is, let's call this vector v1. Then the x component of v1 is going to equal 5. Similarly, the y component of v1 is going to equal 2. So v1 in the y direction equals 2. What we're essentially saying here is that this vector can be broken up into 2 pieces. So we can write this as v1 equals 5 times the x unit vector plus 2 times the y unit vector, where the x and y unit vectors are orthonormal, ortho meaning they're 90 degrees apart from each other, and normal meaning they have a length of 1. And these are our basis vectors. So any vector that we write can be seen as a combination of these things. So I'm writing a new vector here, 3, negative 4, 3 comma negative 4. And I'll plot that here. So this is going to be my second vector, v2, and I'm giving it the components that I just specified. So it will have a length of 3 in the x direction and negative 4 in the y direction. And now when I add vectors, I add them tip to tail. So I'm shifting vector 2 over so that it starts at the tip of vector 1, and when we sum these vectors, we get a resultant vector, v1 plus v2, which is the diagonal of a parallelogram. And we add v1 and v2 by components. So v1 plus v2 will equal 5 plus 3, close parentheses, times the x unit vector, plus 2 minus 4, close parentheses, times the y unit vector. We end up with 8 times the x unit vector minus 2 times the y unit vector. And I'll just plot that there, 8 comma negative 2. This brings us to our discussion of what's known as the complex plane. So the complex plane is a lot like our ordinary coordinate plane in 2 dimensions. I'm drawing x and y axes here, but I'm going to label them slightly differently. The x-axis is going to be the real axis, and the y-axis is going to be I times y, the imaginary axis. And if I have a complex number z equal to a plus b times I, I'm going to draw z the way I would draw a vector, and I'm going to treat a and b as the components of that vector. So I'm going to write it in a kind of coordinate notation, parenthesis a comma b, close parenthesis, and I can plot that complex number. For example, if z equals 2 plus 4 times I, let's say, then I'll plot that as the point 2 comma 4 on this complex plane. And let me try to draw that. So marching out over to 2 on the x-axis, on the real axis, and up 4 on the imaginary axis, there's my point, there's z. I can think of z again as a vector, and I'm going to draw the arrow showing that. So this is my complex number z equal to 2 plus 4i. The real part is 2. The real part of z equals 2. That's the length on the x-axis, and the imaginary part of z equals 4. And I can also now define the complex conjugate of z. I had mentioned that briefly before. That's going to equal a minus bi. The complex conjugate would then be plotted by reflecting z over the x-axis. Z bar, or complex conjugate of z, is going to equal 2 minus 4 times I. So the real part is unchanged by complex conjugation, and the imaginary part is negated. And those two numbers are called complex conjugates. And again, complex conjugation in this geometric representation is just reflection across the x-axis. And the last concept I want to define is this concept of the modulus of z. We put an absolute value sign around z, and I think it'll become clear why in a moment. We say the modulus of z equals the positive square root of a squared plus b squared, where of course a and b are the real and imaginary parts of z. And what we're basically doing is treating z as the hypotenuse of this right triangle, whose legs are equal to the real and imaginary parts. That leg is equal to a, that shorter leg, and the longer leg there is equal to b in length. And then we call the modulus of z the length of this hypotenuse. So I'm going to write that over here. The square root of a squared plus b squared by the Pythagorean theorem is the length of our hypotenuse here, and that's equal to the modulus of z. I'm writing that down here, modulus. The modulus gives us a notion of magnitude, a notion of length in our complex number system. Well, thank you very much for watching today's video, and please do not hesitate to message me with any feedback that you would consider helpful. Thanks, and see you next time.